Good morning, guys. Today our topic is series resonance circuit. Okay, so just want to please join this class. So series resonance circuit means there must be inductance capacitance in series with R, and you can see this circuit. Inductance and this is capacitance, and the supply is given to this circuit is AC. Okay. So this is R, this is R, this is L, and this is C. So in a series resistance circuit, in a series resistance, series resonance circuit, it conditions when no resistance is there, or you may say the resistance is very low. If the resistance is there, then circuit will be damped. If there is no resistance is there, then it is this is a resonance condition. But if this is there is a resistance, then circuit will be damped. Okay, so but if the resistance is present, then it is start damping, then the circuit, it current will be damped to a steady state. Okay, so this is the series resonance. In the series resonance, we can see this is the VR, this is the VR, this is the VL, this is VL, this is VL, and this is VC. Okay, VC. And the current is flowing, that is I. Okay, and this is VS. And or you can say this is the total V. Here I is just I is just like V by Z, this V by this Z, this is V is or V, whatever it will be. Somewhere it is denoted as the source volt, somewhere it is denoted as the V only. Okay, and this is the already ampere. Okay, so here Z is the impedance, the equivalent impedance, or you may say that is the equivalent impedance. P is doing disturbing. Equivalent impedance. Now we can write that is Z equal to R Z equal to R plus Z equal to R plus J omega L. Okay, and we can write 1 by a J omega C. Okay, now we can multiply both sides, this J and J. What happens then? R equal to R plus J omega L. This would be minus J, because this JJ minus J, then omega C. Okay, omega C. So J equal to R plus J XL minus HC. This is called alt X total. So we can write R equal to J into X. Okay, where XL is the inductive reactance, XC is the capacitive reactance. We can write that for better convenience. XL equal to omega L, and XC equal to 1 by omega C. Okay, so J equal to R plus G X. And thus I can be given, you can see, I can be written as V by R plus J X XL minus XC equal to V by R plus X ampere. So now we can see the voltage vector diagram. Look, in this case, if this is a VR, then it is a I. If so, this is VL and this is I and this is 90 degree. This is also 90 degree. This is I and this is BC. Okay, so we can write that this is VR, this is VR, and this is VC, this is VC, okay, and this is ultimate V. So in the resonance condition, when when XL, we can see XL equal to XC. At that moment, the resonance condition obtained. So this obtained by either decreasing the supply frequency when XL would be decreases and XC would increases, or by the increasing the supply frequency, it making the XL to the increasing and XC to the decreasing. Okay. So when XL equal to XC, then Z equal to R plus G, that is 0. So it is ultimately yields, this is the R. So at the resonance frequency condition, Z equal to the ultimate impedance. Impedance is the ultimately the resistance. So I0 equal to V by Z equal to V by R ampere. Okay, and I0 is the current at the resonance condition. Okay. So cos phi power factor. What is the power factor? Power factor cos r by z equal to r by r equal to 1. So at the resonant condition, power factor is the UVT. Okay, just remember that. The expression of the frequency of resonance can be obtained by as the following. Let omega or f0 be the frequency at which xl equal to xc. Here xl equal to xc. So omega l equal to omega c, or you can write omega square equal to, look, this omega coming to here, so it is coming and this is coming lc. So omega equal to 1 root under lc. Okay, this is called radian per second. Okay. So if this frequency is 1 by 2 pi root over of LC. Okay, this is hertz. Okay. So the vector diagram at the resonance condition is vector diagram as the resonance, and this is the voltage vector diagram. This is the resonance condition. This is the VL. This is the VC. VC. This is the L. This is the L. And this is, sorry, this is not L, this is a current. This is C. Okay. And now we have to know the properties of resonance conditions. It is some properties are there also. And the first property is applied voltage and the resulting current are in the phase. Look, first property is applied voltage, and the phase current are in the phase. I and V is the in the phase. also mean that the power factor of the RLC series resonant is unity. Okay, we have find out it, that is power factor is PF is, that is PF is 1. Okay. Next point is the net reactance is 0. The net reactance is 0. That means X equal to 0 as XL equal to XC. Okay, and the current in the circuit is maximum and is V by R ampere. V by R, but this is I is the maximum. Okay, and the resonance circuit, it has got the minimum impedance and the maximum admittance. So in the series resistance, it is react as an admittance. Okay, now we can see the graphical representation of it. Look, the impedance of the series circuit and this is XL, this is XC, and this is frequency. And this point is F0. Okay, and this is XC. Okay. And this is R. So from this point, we can realize that this is a variation of XL and XC with the frequency. So the impedance of the series RLC series, it could be given as put under r square omega L. So So when the frequency is zero, f is zero at the zero frequency, both the Xc and the Z are the infinitely large. When the f is zero, means resonant frequency, or this is called resonant frequency, then this Xc and Z, then Xc and Z are infinitely large. Then Xc and Xc and Z is infinitely large. Okay. Now, XL is zero because at the zero frequency, the capacitor acts like an open circuit and the inductor acts as a short circuit. Okay. And at the frequency increases, you can see as the frequency increases, then the HC is decreasing because you know this is F is underneath the this here underneath the one, that's why it is decreasing, and XL is just multiplied with the L. So XL frequency increases, the XL also increases. Okay. And since Xc is greater than XL at the frequency below this resonant frequency, and X, and then after that here XL is greater than the Xc. So at the resonant frequency, if XL equal to Xc equal to XL, or XL equal to Xc, whatever may be, and Z equal to R. So in this point, at in this point, Xc equal to XL, okay, and Z equal to R. But whenever it is just means the greater the frequency, that is the less than here, means resonance frequency, then Xc is greater than XL. Here Xc is greater than XL. But in this region, means above the resonance frequency, XL greater than Xc. Okay, so this is the inductive current. If you get this current, whenever you go for the numerical, you can realize this thing. 10 hertz before and 10 hertz above. So here, this is the inductive current you get, and here you get the capacitive current. Okay. So at the frequencies above the resonance, if XL is larger than XC and causing Z to the increasing. Okay, here Z will again increase. And now we have to consider the phase angle, because if the power factor is going to unity or going to under the unity, then we get some problem. That's why we have to consider these things. Look, this is your uh, this is your theta, phase angle theta, and this is the 90 degree. This is the positive 90 degree. and this is the negative 90 degree. So if this is a resonant frequency, if R, resonant frequency is if R, then we get this type of curve. Okay, so you can see when above the resonant frequency, so this is the inductive. So I is lags voltage source, or I told that this is the source voltage or this is the only voltage. This applied voltage, and this is the capacitive area, capacitive zone. So this is I leads Vs. Okay. So this is the point. So at a frequency below, you can write down at a from this picture you can remember this. Don't need to uh, just memorize this. Just memorize this graph. So above the resonant frequency, I I lags Vs, and below the resonant frequency, I leads the Vs, because this is the inductive zone and this is the capacitive zone. Okay, so a frequency below the FR, I leads Vs because the capacitive reactance is greater than the inductive reactance. Why this is Vc is sorry, Xc greater than XL, and in this region XL greater than Xc. Okay, this is the main things. So my question is that if our frequency, our rated frequency for India, this is 50 hertz, 50 hertz. What happens if it is lags? It is downwards to 40 hertz. Sometimes it may be provided 40 hertz, or sometimes it may be provided 60 hertz. What happens? What happens? This 50 hertz maintained because it is our resonant frequency. If just think this is a resonant frequency, what happens? Any idea? Because if 50 hertz yields you the unity power factor, means it say assume it's a resonant frequency, then what happens? Then if we get 40 hertz, then power factor will losses means goes down to the unity, and if it is going to the higher frequency, then it is going to the unity. So you can get an example, mathematical example, then you can understand these things. Okay. And another thing, the Q factor. So Q factor is here. Q factor is the storage factor in a series resonating circuit. Q factor, or you can say this is the quality factor. Q factor or the quality factor. Quality factor, it is defined as the ratio of the voltage across the inductor or the capacitor to the applied voltage. So Q factor for inductance is the VL by V, and Q factor, this is for L, this is for L, and Q factor for the C, it is VC by P. So we can write down that is Q equal to VL by V for the inductor, or we can see VL by V. We can see, just you can write down this I naught into XL by and I naught into R. Okay. So we can write down omega naught I into XL. This is the omega naught L. Okay. And it is given by the R. Because this I was nullified, this XL equal to omega naught L, and this is the R. So Q factor depends on this XL. Okay. Same way, we can write down the Q factor is, we can write down this VC is I naught HC divided by, what is this? I naught into V means I naught into R. Okay, so it is just nullify. Then we know X equal to 1 by omega naught, 1 by omega naught C. And this is R, so it is coming over here. Okay, so in this way we can write this. Q is the 1 by omega naught CR, or this omega means 1 by root over 1 by root over LC, and this is C into R. Okay, ultimately we can write down 1 by R into L by C. So this is, we can write down in this way also. Same things we can also write over here. Q equal to 1 by R root over of L by C. So this is the relation between Q factor. So guys, I am going to stop here. Next, I am going to start another meeting so that we can solve a numerical on this resonance circuit. Then we will go for the parallel resonance circuit. Okay, thank you.